All right. Well, good morning and happy Monday. Time is ticking right along. It's week 7 already, and um, and also, yeah, thanks for everybody for meeting with me for your proposal meetings. Um, a lot of. I think there's going to be a lot of neat, interesting projects during week 10. There's an option to do a presentation for some extra credit points, and I'll talk about that. And I think you guys will have fun seeing some of the projects that your classmates have done. Some of you I instructed we need to have a follow up meeting, and so if we haven't actually scheduled the time of the follow up meeting, please make sure you do schedule a follow up meeting with me, and you're also more than welcome to come by during office hours, even before your follow up meeting, to kind of just make sure things are, getting resolved and fixed and things like that. So don't hesitate to stop by office hours. And then yeah, I'll see you guys at the follow up meeting. And if we haven't actually scheduled the time and date of the follow up meeting, so I I think we scheduled it. I put it in the comments as far as the feedback on the proposal questionnaire. And so if you don't see an actual time and appointment in the comments there, that means we don't have a follow up meeting scheduled in the book. So please make sure we schedule one. Okay. All right. Anyway, today's lecture, I want to talk about identifying outliers. Okay. Just because in a lot of data sets, sometimes some of the most interesting stories are stories behind outliers. Okay. Kind of like, how did this individual get such a huge number, or something like a number that's so different from everyone else? And you might end up deciding to exclude that individual or those individuals from the rest of your analysis, and that could be a justifiable decision. You might continue to include them in your analysis. That's also perhaps a justifiable decision. You want to be able to kind of defend every choice you make. But the question of, like, how do we even determine what an outlier is in the first place is kind of a question that's, I think, worth discussing, right? Like, who counts as an outlier? This one's a little bit higher than everyone else. Are they an outlier? And things like that. And so there's some ideas and notions, and this is not going to be like the definitive way of defining and identifying outliers, but it will certainly point you in the right direction and give you some, at least tell you what other people have done, and things like that. So yeah, as you do your projects and you work through your data, if you do see some outliers, it's probably worth investigating those individual events or things like that, right? So there could be like, this is the one year, right? Like, if, I don't know, for example, you're looking at like airline travel numbers or something, and then like there's a huge drop in 2020 and 2021, and we can identify and say, yeah, that was this unprecedented moment in the pandemic, where basically worldwide travel and stuff shut down and things like that. And as far as doing regular old analysis, yeah, maybe we should exclude those years, but there's certainly an interesting reason in this story behind that. Okay. And a lot of times with sports and things like that, it'll be like, oh yeah, this individual stood out so much, they ended up having to change the rules after this person, or whatever, right? So there's often kind of interesting things to go along with outliers. So anyway, basically, one of the ideas, or one of the things why somebody stands out as an outlier is because the outlier, that individual or event or instance of the thing, stands out from what we would consider the normal amount of variation, right? We understand that there's variation where things, everybody's different. Some things are larger, some things are smaller, and things like that. But then the outlier is like the individual that kind of really stands out compared to what we might consider like normal amounts of variation, right? So it's kind of just like, if you see somebody who's 6'4", we'd say, oh yeah, that's a tall individual. I don't know what 6'4" is in centimeters, but we'd say, okay, that's a tall individual, but it's not super unusual, okay? Whereas if we see somebody who's like 7'4", we'd say, okay, that is really, really, really tall. Probably not later. Now I want to know, okay, 6'4". What is it? 193. Okay, and then if we do 7'4", 223, right? So one is, both are tall, but one is like, okay, that's an outlier. Okay. All right. So we have a way to measure variation. Okay. Variation is a measure of how similar. Now I just had deja vu. Did I already do this? I don't know. This slide?
Yeah.
I did this slide already. 3 weeks ago. Okay. All right. Standard deviation. Okay. Yeah. Okay. Sorry about that. All right. So anyway, yeah, we talk about like, okay, are the ages spread out in the second grade classroom because everyone's like the same age? They are not. You have tiny variation, little variation, college students, medium amount, waiting room at the urgent care, whatever. Lots and lots of variation. And so we measure that using something like the variance and the standard deviation. And these are the formulas that we use, okay? So as far as calculating the definition of the variance that we have, okay, is we can talk about the deviations from the mean, and then we say what is like the average deviation, or what in our, for variance, it's the average of the squared deviations. So if we have 1, 2, 3, and 10, the mean of these four numbers is 4, and we can say, okay, 10 is 6 units away from 4, and its squared deviation or squared distance is 36. We do this for all of these things. We add them up. We divide by n minus 1, okay, for reasons beyond the scope of our course, and we get our variance, 16.67, okay? If you major in stats and data science, or if you major in data theory, you'll cover the reason why to make it an unbiased estimator in, I think, 100B, okay? So anyway, we can get the standard deviation, the variance, and things like that using R, using the function var or SD. Okay, var will give us the variance 16.67, which is the exact number we have here, and standard deviation 4.08. Okay, is the square root of 16.67. Okay, and so these are ways for us to kind of measure how much spread we have. And so the other example I like to use is just kind of like, okay, you think about these two families with these children. Both families have 5 children, and in both families the average age is 9, but in one family the ages are much more spread out, and the other family the ages are not as much spread out. Okay, and so how do we compare these things? Well, we can calculate the standard deviation, we can calculate the variance for these things, and so yeah, mentioning just the number of children and the mean age doesn't give the full picture. So we calculate the standard deviation of ages for one family. Okay, the square distances are 64, 36, 0, 16, and 100, and that standard deviation is 7.35. And then for the Cook family, square distances are 41014, and so its standard deviation is only 1.58, right? And so, you won't do this by hand. You'll just kind of take the number, you'll create a vector, or in R, you'll have a data frame, and you'll just kind of select that column and pull those values, okay? And then you'll call standard deviation on that vector of values, okay? To get these things, and getting different standard deviations gives you a sense of kind of how much variation we have. So then, for example, if we're talking about, say, the penguins data set, okay, we can take a look at any of these columns, bill length, bill depth, flipper length, body mass, or things like that, and we can say, all right, let's calculate some of the standard deviations and things like that. All right, so here what I'm going to do is I'm going to take bill length and bill depth, all right, and we're going to take a look at these numbers, and we'll create a kind of a plot based on them, okay? And so as far as bill depth goes, this is the distribution of bill depths. So the average is around, 17-ish, 18, okay? And then this is the distribution of bill length. And we can see not only is the average higher, so for bill length, the average is probably around 45, something around there, but we see there's more spread, okay? The variation for bill length varies anywhere from kind of on the low end, maybe around 35. I'd say most of our values are going to be between 35 and 55. The extreme longest is around 60, and the extreme shortest is around 31, 32. Okay. Whereas if you look at, say, bill depth, the shortest looks to be around 12, and the longest to be around 22. So we have a kind of much smaller range. And if we calculate standard deviation and variation, we'll see much smaller standard deviation here and a much bigger standard deviation there. Okay. Let me give you your first view quiz answer, which is the letter C. C as in cat. So we can calculate, standard deviation summary values here. So I'm taking penguins. I'm going to call summarize on this, and we're going to just take that column bill depth and calculate the mean of it. We'll take the column bill depth and calculate the standard deviation. We'll do the same for bill length, calculate the mean standard deviation for bill length. So what we see is the average bill depth is 17.2. That aligns with what we see here. And the average bill length is 43.9. Okay, so eyeballing, I was saying around 45, and it's what, 44, 43.9. Okay, and then if you look at the standard deviation, indeed, it confirms what we see. Standard deviation for bill depth is around 1.97. Standard deviation for the length is 5.46 for the bill length. Okay, so more than double that. So more than kind of twice the spread there. So one of the measures that we have to help us decide if something is an outlier or not is to use something called a z-score, right? So a z-score is how far an observation is from the mean, and we express that distance in standard deviations, okay? So basically, you have some observation, and you say, okay, well, how much higher is it, or how much lower is it from the mean? You're just going to calculate the distance between that observation and the mean, okay, x minus x bar. But then you take that difference, and then you divide by how big a standard deviation is, right? So it's kind of just like, what's the difference between two people's heights? And then maybe you'll say, okay, but I want that difference expressed in the number of feet, right? So you say, okay, this person is 6 inches taller than the other person. Each foot is 12 inches. So that person is half a foot, right? And basically you're just taking the difference between the two numbers and then you're dividing by the size of whatever you're using. In our case, the foot was 12, but here we're going to use standard deviations. And when, so we can ask something like this. If we have a penguin, an Adelie penguin, with a bill depth of 20 millimeters, or a Gen 2 penguin with a bill length of 55 meters, which of these things is more unusual? This is not, I don't know if anybody actually cares about these penguins, but this is kind of like, all right, without further information, we can't really answer this question. We would need to know, like, what's the average bill depth of an Adelie penguin? What's the average bill length of a Gen 2 penguin? And then not only that, but we would also need to know the standard deviation, okay? So we're gonna, let me load up the tidyverse. Okay. So what I first need to do, okay, is I need to get the summary statistics for each of these species, okay? And we're going to calculate the average bill depth and bill length and the standard deviation of the bill depth and bill length. So let me go ahead and just execute this. So we'll take penguins, we're going to group by the species, and then we're going to calculate the mean and standard deviation for bill depth and bill length, right? So my hope is by now we're starting to feel comfortable reading the syntax and the code here, and we can understand, like, if we read this and read this, we understand at least this is going to be the form of the output, okay? Oh, you have a midterm, or not midterm, just the one exam for the class. That will be next week. So I will give you, I still haven't finished writing it, but I will give you more information about that on Wednesday, okay? So then you can prepare accordingly. I don't know. It's like, it's, the thing about practice problems is, like, I can write some, but then students will complain, like, oh, no, the actual exam was nothing like the practice problems. So I don't know. Yeah, I still have to finish writing the exam itself, and then writing additional practice problems on top of that is a challenge. So I don't want to make any promises, but I will tell you what you can expect. Okay, I'll tell you what kind of stuff you can expect. Okay, so anyway, this is what we have, and so we're gonna go back and we're gonna ask, okay, the Adelie penguin with a bill depth of 20 millimeters, okay? So if we look at these numbers, all right, so we're gonna do z-score. I'll do Z Adelie 20. And so what we wanna do is we wanna do 20 millimeters minus the mean bill depth, okay? Which I'll do is 18.3, or actually perhaps I'll call this, I don't know, the sum table. Okay, summary table will be that. And then so I can, if we look at the value, if I want to extract this value, this is going to be first row, second column. So I can do summary table 1, 2, and this will I can extract that value. I can call pull on it, and we'll get, like, the full value, not rounded off. Okay, so this is going to be the I don't know, the mean Adelie bill depth, which is a terrible abbreviation there. Okay, so we'll do that, and then if I want to get the standard deviation out, 1.22, that's the first row, third column. So I'm going to go to my summary table, and I'll say I want to get the first row, third column, and I want to pull that value. Okay, and we'll get 1.21665, and that will be, I guess I'll call this the standard deviation of Adélie bill depth. I don't know if that's any better. It's not. Okay, and then so we're going to take the difference between our observation, x minus the mean, and we'll take that difference and divide by the standard deviation. So my z-score is going to be 1.359177. Okay, and then we want to do the same thing for a Gen 2 penguin with a bill length of 55. So we'll do z Gen 2 55, and I need to get basically the same numbers, but for bill length on Gen 2. So we're going to say mean bill length, standard deviation bill length, and this is going to be Gen 2. I don't know. Okay, so we want Gen 2 is row 2. Gen 2 mean bill length is row 3, column 4. And then Gen 2 standard deviation of bill length is row 3, column 5. Right, so that number is 47.505, and then this one 3.08. Yeah, 3.081857 if you want all of these numbers. Okay, so the 55, we're going to do 55 minus the mean Gen 2 bill length divided by the standard deviation of Gen 2 bill length. So comparing these two numbers, as far as the Adélie penguin, its z-score for 20 millimeter bill depth is 1.36, and for the Gen 2 55 millimeter bill length, it's 2.43. So as far as z-scores go, the Gen 2 penguin has a bigger z-score. This is like the more unusual observation. Okay, so we're calculating these numbers, and I think I did the math here. 1.359 versus 2.433. Okay, and that's what we have. If I plot these, okay, so here I said, okay, let's plot bill length, bill depth. We're going to put the value along the x-axis. We're going to color them differently based on the name, whether it's bill length or bill depth. We'll make a histogram, and then we're going to create a facet grid based on the species. Okay. So can we imagine what this plot will look like? We're going to have a plot that looks like this. So we have the different species, Adélie, chinstrap, Gen 2, and kind of the points that we're looking at is we said, which one's more unusual, Adélie with a 20 millimeter or Gen 2 with 55, right? So if we look at 20 millimeters for Adélie bill, that's right here, this line for 20 millimeters. So we can say, it's on the higher side, but it's not super unusual, okay? 20 millimeters for a Gen 2 bill depth would actually be like super unusual looking at this plot, okay? But 20 millimeters up here, not that unusual, okay? But as far as bill length goes, the 55, yeah, that's like one of the top, I don't know, however many, right? So there's just a couple observations more extreme than 55, okay? Actually, 55 on Adélie would be even more extreme because there's like nobody up there. But here we're comparing the 20 millimeter Adélie with the 55 millimeter Gen 2 here, okay? And so, yes, the plot, I think the visualization gives us kind of a more intuitive understanding of saying like, okay, which one's more unusual, the 55 with Gen 2 or the 20 millimeter bill depth for a deli? And we look at these plots and we look at that, and that gives us kind of an intuitive sense. But if you needed something kind of more precise, where you want to have a number, you know, and sometimes it might be close, right? Which one's more unusual? Like, what about 55 for chin strap versus 55 for Gen 2? Like, which one's more unusual? That one, that might be tough to quantify. And so being able to use like a z-score to give you a number could be useful here. So yeah, if we look at 55, so for chin strap, the 55 z-score is definitely going to be smaller than the 55 Gen 2 here, because here the mean is lower over here and the standard deviation is smaller, and here the mean is higher, closer to 55, and the standard deviation is even bigger. So the numerator will be smaller and the denominator will be bigger. So you'll have a smaller z-score. I don't know what it is going to be off the top of my head, but we can just looking at this, I know the x minus x bar is going to be smaller for chin strap and the denominator is bigger, so it's going to be give you a smaller z-score there. Okay. Whereas 55 up here, it would be crazy because it's the x up there is really huge. The difference between x and the mean is really huge, and the standard deviation is even smaller, so you have a smaller value in the denominator, which makes the z-score even bigger, all of that, okay? So, you know, just different species, different groups, which one's more unusual. So z-score is a way for you to, is like the tool that you would need to use to compare apples to oranges, right? So you have different things, different groups and different measurements, but you still kind of want to get a sense of like which one's more unusual. You can use the z-score there, okay? Oh, this is just to kind of drill it home. And I just said, all right, based on our z-scores, we said, okay, the Gen 2 penguin with 55 is more unusual than the Adelie with a 20 millimeter bill depth. And just to kind of really drive it home, I said, all right, what if I just look at all of the Adelie penguins, and I said, how many have bill depths greater than or equal to 20, right? So I create a new column called depth over 20, and this is, when you have a comparison here, a comparison statement is going to be either give you a true or a false, okay? So true if bill depth is greater than 20, false if it's not. So we mutate that. I'm going to just select that new column I just created, and then I create a table out of it. And so we could see out of all of the different Adelie penguins, there were 18 penguins where this was true and 133 where it was false. Okay, so as far as a proportion goes, 18 divided by 133 plus 18, that's around 12% of penguins, Adelie penguins, have bill depths over 20 millimeters, okay? Greater than or equal to 20, okay? What about Gen 2 penguins? How many Gen 2 penguins have bill lengths over 55, okay? And here we only have 3 out of 123, okay? So what's that? 3 divided by 123. Okay, around 2%, 2.5%. So definitely much fewer penguins, okay? And so this is code that I've written to just really emphasize this, the fact that the z-score, it's not just something we make up, all right? But it actually will reflect when you calculate the z-score and you say like, okay, the z-score here is 2.43 and it's bigger than the z-score over here, 1.359, it will also reflect in the data, okay? There is just kind of this guidelines, okay? The empirical rule, all right, is that if you have data that's unimodal and symmetric, which these ones I would say overall, this is unimodal and symmetric, unimodal and symmetric? We talked about unimodal and symmetric? Okay. Oh, so now, because I teach all of these different stats classes and like they all kind of like blur together, and I'm like, I think we talked about it, but then sometimes okay. I mean, we might say is bimodal, but overall, pretty much unimodal. I mean, sure, there's like a little dip here, but we would just say like overall, this is like one peak right here, unimodal and symmetric. This is pretty close to unimodal and symmetric if we just ignore this small dip here for whatever reason that exists, and also something like this, right? I don't know, maybe there's something actually genuinely happening here. Maybe this is bimodal, but you know, looks close to symmetric, okay? So if you have something that's unimodal and symmetric, then these guidelines are gonna be pretty accurate, okay? So most of your values, okay, around 2/3, okay? And if you wanna be a little bit more pedantic and precise, we can say 68%, about 68%, but generally around 2 out of 3 observations will have a z-score between 1 and -1. Okay, so most, like if you calculate a z-score, most people, whatever it is, if it's a unimodal, like a height, most people are going to have a z-scores between 1 and -1. Okay, average, if you're exactly average, your z-score is 0. Okay, if you're exactly average, your z-score is 0. If you're a little bit above average, maybe plus 0.7. Okay, if you're below average, maybe -0.3. 2 out of 3 people, 2/3 around 1 and -1. Okay, and then 95%, so that's like 19 out of 20 people. So only like 1 in 20 people have z-scores more than 2 or more negative than -2. But 95%, the vast majority, will have z-scores between 2 and -2. Okay, so only a small percentage, about 5%, will have a z-score greater than 2 or more negative than -2. Okay, and then if you go to 3 and -3, that covers almost everybody, 99.7. So it's like really extreme cases will have z-scores greater than 3 and z-scores more negative than -3. Okay, so this is one way for you to identify outliers. Certainly, if you have any observations, if you have a unimodal and symmetric thing, any observations with z-scores greater than 3, that's certainly going to be an outlier. The z-scores more negative than -3, that's going to be an outlier. Okay. And then you can kind of draw some arbitrary line. You probably don't want to say 5% are outliers, but if you go like z-scores over 2.5, 2.7, something, you know, just some arbitrary value, okay, that'll give you a sense. But you can safely say anything over 3 is an outlier. Anything more negative than -3 is an outlier. Okay, if it's unimodal and symmetric. If it's highly skewed, then you're going to have these really big z-scores for everything on the skewed side. So I don't know. Like, for example, income, it's like so skewed. At what point is something an outlier? I don't know. Like over $1 million, is that an outlier? Or does it have to be like 5, like, you know, what we would consider like an outlier for income or something, annual income, is just because it's so skewed, right? And then $1 trillion, I don't know, right? So what happens? Okay. All right. So we have also another way for us to identify outliers is using box plots. Okay. So, you know, when we create a box plot, okay, the box is, the ends of the box are drawn at the first quartile and third quartile. So these correspond to the 25th percentile and 75th percentile. How many answers have I given you? 1. Okay, I'll give you the second. The second answer is B. B as in bear. Okay, B. So when we draw a box plot, the box shows the IQR, and the IQR is the difference between the 25th percentile and the 75th percentile. Q1 is your first quartile. Q3 is your third quartile. So it's like first quarter is below the first quartile. 25% are below the 25th percentile. 3/4 are below the third quartile, and 75% is below the 75th percentile. And you can have like other things like deciles, and that would be the second decile would be the 20th percentile, 2/10, 2 decimals. I don't know, whatever. Okay. So let's say we have this data set on plant growth and we put them in order and we figure out, okay, here's my median. So if you have 14 numbers, the median is going to be the spot where half of your values, 7 are smaller, 7 are bigger. This is like a trivial data set, but this is just to illustrate the point. On the computer, you would just say, hey, find my median, okay? And it'll find it for you. But here we'll say, okay, give me the median here. If I count 7 numbers in 1, 2, 3, 4, 5, 6, 7, I get 3 through 9 on this side. And then I've got 7 numbers on this side, 10, 10, 10, 10, 14, 20, 21. And so basically it's the spot between the 9 and the 10. So halfway in between there, 9.5. My median is going to be 9.5. And then now that I have my lower half of numbers, okay, yeah, and R, you just say, hey, give me the median. It says 9.5. Okay, now that we have this, we can say, all right, give me what's the halfway point of these things, and we're going to get 7. Okay, so the halfway, the median of these 7 numbers is going to be 7. Okay, and then the median of these 7 numbers over on the right will be 10. So my Q1 is 7, this value, and my Q3 is 10. Okay, so my IQR, 10 minus 7, we get a IQR of 3. The range is the max minus the min, range of 18. But we can use this, we can use the IQR as a guide for helping us determine outliers. And the box plot method is to go basically 1.5 IQRs above Q1, or below Q1, and 1.5 IQRs above Q3. So there's something called a 5-number summary, and this is just like, if you have like a guess, imagine like you're empty and your gas, it's basically like, where is the halfway mark, where's the quarter tank, where's the 3/4 tank, right? So you got the minimum, first quartile, median, third quartile, maximum, and that's basically the spots that correspond to the 5-number summary. Yeah, question?
Is there like a certain kind of z-score that corresponds to like box plots, like where the outliers start, like once like 5, 5, 5, 12?
Yeah. So if we go 1.5 IQRs above, let me see. So yes, so let me P norm. Sorry, actually it's Q norm and 0.75. So my IQR is going to be, I just do 2 times Q norm of 0.75. I should know this off the top of my head, but I don't remember. So if I do Q norm 0.75 plus 1.5 times the IQR, 2.7. So so that would be the z-score. The z-score that corresponds to 1.5 IQRs above the third quartile would be 2.7. Okay.
This is for exactly.
So this would be if it follows the exact normal distribution. So obviously, if things aren't exactly the normal distribution, give or take, but the rules for box plots is around basically z-scores of 2.7. And so what's let me see, if I look up negative 2.7, you're going to get 0.003. So if I multiply that by 2, so there, if you look at the amount beyond 2.7, you're going to get around 7 in 1,000, versus if you use z-scores of 3 as your threshold, you get around 0.00269. So around 2.5 in 1,000. So it's a difference between the top 7 in 1,000, like top 0.7%, or I mean the most extreme 0.7. So that's on both sides, like the top 3.5 and the bottom 3.5 people, versus the top 2.5, or top 1.5, or something on each side. Okay, so. So anyway, yeah, that's the 5-number summary. This will give us this, and then you can also ask summary on a vector. So again, you probably won't type it up. You'll probably just do a select the column and call pull, and then you would call summary on that thing or something. And this will give you the 5-number summary as well. Okay, and then our outliers, we draw these fences where basically 1.5 IQRs below Q1 or 1.5 IQRs above Q3. If it's perfectly normal, yeah, that would, I guess, correspond to z-scores around positive 2.7 and negative 2.7. But this is another way for us to determine outliers. And so with box plots, you can use it for skewed data, right? So z-scores, once it gets like really skewed, things start to get a little bit wonky. And so box plots, this can be used as a threshold for trying to figure out what counts as outliers in skewed data. So here my IQR is a 3 and my Q1 is 7. So I would do 1.5 IQRs below Q1. So 1.5 times 3 is 4.5. 7 minus 4.5 gives me 2.5. So that's going to be my threshold. Anything that's below 2.5 I would consider as an outlier on the lower side. But in my data, I don't have anything lower than 2.5. My smallest value is a 3. So I don't have any outliers on the low side. Okay, but I do 1.5 IQRs above Q3. Q3 is 10. The IQR is 3, so 1.5 IQRs is 4.5. So 10 plus 4.5 gives me 14.5. And I say, okay, any value above 14.5 counts as an outlier. So here I would get 20, 21. Those are the values above 14.5. Yeah, question. 14 is, so the fence is at 14.5. So anything bigger than 14.5. So 14 just barely makes it under 14.5. So 14.5 is not an outlier. It's pretty close, but it's still below that threshold. Just, and then again, this is an imaginary line. There's nothing like super, this is an arbitrary point where we just said 1.5. That sounds like a good number, right? Like there's no, if the statisticians all agreed, like, oh, let's use 1.7 or 1.3, like they could have picked that number, but over time they say, yeah, 1.5, that seems pretty good. 1.5 corresponds to a z-score of 2.7. Yeah, that seems reasonable. And that's kind of the just the established thing. Now you look at your data and you go, oh, you know what? I've got something that's only 1.4 IQRs above Q3. Does that count? If it feels unusual to you, sure, throw it in there and say, yeah, this one feels different, okay? There's not, this isn't like a hard rule, but it's the idea of, all right, I see a bunch of stuff. You need some arbitrary line where you say, okay, more than this, that's too much, right? I don't know, right? And because we have 5 fingers on our hand, like we have a lot of things that are just arbitrarily so, right? So, you know, there's still kind of a, I don't know, whatever. Okay, so anyway, this is what the box plot looks like. When you call box plot in ggplot, it follows these rules. And so the whisker goes to the largest point that's not an outlier, in our case 14, and then the ones that are above 14.5, the 20 and the 21, they get represented with dots, okay? And yeah, the whisker on the left-hand side goes down to the smallest point that's not an outlier, which would be 3. And that's where it goes. Here's our box. The width of the box goes from 7 to 10, and then you have a line down the middle at 9.5. for a box plot. So here, if we do it for the penguins, okay, looking at bill length, we get the IQRs, we get the whiskers, and so we see as far as the different penguins go, there weren't any outliers for bill length, with the exception of Gen 2, right? This one, I guess at 59 millimeters, is an outlier as far as the bill length, and that one's considered unusual. So if you look at the Gen 2, the bill length, the IQR goes, I don't know what it is, it goes from around 46 to 49, 46 and a half, I don't know, 45 and a half to 49 or something around there, okay? And then we go 1.5 times that, and this is like the upper end. So 55 millimeter bill length is on the large end, on the long side, but it's not yet considered an outlier. But I guess 59 would be considered an outlier, using kind of box plot rules. And so, you know, this is probably a legitimate thing. There's just a Gen 2 penguin out there going around with a really long bill, and I don't know if that's a point of pride for penguins, but you know, as far as the penguins they observed and measured, there was no penguin that had a bill length longer than 59 millimeters, and that one is unusual compared to all of the other penguins and something like that. And I don't know, in your data set, you might have an individual or an observation that is an outlier as you know, identified as an outlier using kind of box plot method. But you know, who knows? Let me see. I wonder if I could do penguins group by species. And can I call summary? I'm not sure if I can. Oh, I can. Okay, so no. I don't get it. All right. So I would have to calculate the IQR for each of these things. So I'd have to do penguins, filter, species equal Gen 2, and then select, what did I want? Bill length. And then we'll pull it, and then we'll call summary on it. Oh, I have to pull parentheses. Okay, so we get Q1 is 54.3, Q3 is 49.55. So what is my IQR? So 49.55 plus 1.5 times the IQR, which is 49.55 minus 45.3. Okay, and so the upper fence is 55.925. So any penguins with bill lengths 55.9 or lower in Gen 2 is not considered an outlier. But again, the max penguin length, bill length was 59.6. That one is an outlier. And if I take the full and I sort it, the longest, so we had bill length 55.1, 55.9. So 55.9 is close, but not an outlier yet. 59.6 is above the threshold and is considered to be an outlier. And so that's the one. So this one's 55.9 and this one's 59. Yeah, so this is the one there. Okay, so I think being able to identify outliers and look through your data and say, hey, these ones do seem kind of high or low or whatever is good. And try to see if you can identify the story behind it, especially if you have anything where it's like associated by years. You can say like, oh, why is this 1 year different? And see if you can find something in the history about it. Okay, that's it for today. We'll wrap things up there. Last view quiz answer is E. E as in elephant. E as in elephant. Okay. That's it. We'll see you guys later.